In mathematical finance, the Greeks are the quantities representing the sensitivity of the price of derivatives such as options to a change in underlying parameters on which the value of an instrument or portfolio of financial instruments is dependent. The name is used because the most common of these sensitivities are denoted by Greek letters. Collectively, these have also been called the risk sensitivities, risk measures or hedge parameters. Use of the Greeks. The Greeks are vital tools in risk management. Each Greek measures the sensitivity of the value of a portfolio to a small change in a given underlying parameter, so that component risks may be treated in isolation, and the portfolio rebalanced accordingly to achieve a desired exposure. See for example delta hedging. The Greeks in the Black-Scholes model are relatively easy to calculate, a desirable property of financial models, and are very useful for derivatives traders, especially those who seek to hedge their portfolios from adverse changes in market conditions. For this reason, those Greeks which are particularly useful for hedging, such as delta, theta, and vega, are well defined for measuring changes in price, time and volatility. Although ρ is a primary input into the Black-Scholes model, the overall impact on the value of an option corresponding to changes in the risk-free interest rate is generally insignificant, and therefore, higher-order derivatives involving the risk-free interest rate are not common. The most common of the Greeks are the first-order derivatives, delta, vega, theta and ρ, as well as gamma, a second-order derivative of the value function. The remaining sensitivities in this list are common enough that they have common names, but this list is by no means exhaustive. Names. The use of Greek letter names is presumably by extension from the common finance terms alpha and beta. Several names such as vega and zoma are invented, but sound similar to Greek letters. The names color and charm presumably derive from the use of these terms for exotic properties of quarks in particle physics. First-order Greeks. Delta measures the rate of change of the theoretical option value with respect to changes in the underlying asset's price. Delta is the first derivative of the value of the option with respect to the underlying instrument's price. Practical use for a vanilla option, delta will be a number between 0.0 and 1.0 for a long call and 0.0 and -1.0 for a long put, depending on price. A call option behaves as if one owns one share of the underlying stock, or owns nothing, or something in between, and conversely for a put option, the difference between the delta of a call and the delta of a put at the same strike is close to but not in general equal to 1, but instead is equal to the inverse of the discount factor. By put-call parity, long a call and short a put equals a forward F, which is linear in the spot S, with factor the inverse of the discount factor. So the derivative dF/ds is this factor. These numbers are commonly presented as a percentage of the total number of shares represented by the option contract. This is convenient because the option will behave like the number of shares indicated by the delta. For example, if a portfolio of 100 American call options on XYZ each have a delta of 0.25, it will gain or lose value just like 25 shares of XYZ as the price changes for small price movements. The sign and percentage are often dropped. The sign is implicit in the option type and the percentage is understood. The most commonly quoted are 25 delta put, 50 delta put, 50 delta call, and 25 delta call. 50 delta put and 50 delta call are not quite identical, due to spot and forward differing by the discount factor, but they are often conflated. Delta is always positive for long calls and negative for long puts. The total delta of a complex portfolio of positions on the same underlying asset can be calculated by simply taking the sum of the deltas for each individual position. Delta of a portfolio is linear in the constituents, since the delta of underlying asset is always 1.0. The trader could delta hedge his entire position in the underlying by buying or shorting the number of shares indicated by the total delta. For example, if the delta of a portfolio of options in XYZ is plus 2.75, the trader would be able to delta hedge the portfolio by selling short 2.75 shares of the underlying. This portfolio will then retain its total value regardless of which direction the price of XYZ moves. As a proxy for probability, the delta is close to, but not identical with, the percent moneyness of an option, i.e., the implied probability that the option will expire in the money. For this reason, some option traders use the absolute value of delta as an approximation for percent moneyness. For example, if an out-of-the-money call option has a delta of 0.15, the trader might estimate that the option has approximately a 15% chance of expiring in the money. Similarly, if a put contract has a delta of minus 0.25, the trader might expect the option to have a 25% probability of expiring in the money. At the money, puts and calls have a delta of approximately 0.5 and minus 0.5 respectively, with a slight bias towards higher deltas for ATM calls, i.e., both have approximately a 50% chance of expiring in the money. The correct, exact calculation for the probability of an option finishing at a particular price of K is its dual delta, which is the first derivative of option price with respect to strike. Relationship between call and put delta given a European call and put option for the same underlying strike price and time to maturity, and with no dividend yield, the sum of the absolute values of the delta of each option will be 1. More precisely, the delta of the call minus the delta of the put equals 1. This is due to put-call parity. A long call plus a short put replicates a forward, which has delta equal to 1. If the value of delta for an option is known, one can calculate the value of the delta of the option of the same strike price, underlying and maturity, but opposite right, by subtracting 1 from a known call delta or adding 1 to a known put delta. D minus D equals 1. Therefore, D equals D plus 1 and D equals D minus 1. For example, if the delta of a call is 0.42, then one can compute the delta of the corresponding put at the same strike price by 0.42 minus 1 equals minus 0.58. To derive the delta of a call from a put, one can similarly take minus 0.58 and add 1 to get 0.42. Vega measures sensitivity to volatility. Vega is the derivative of the option value with respect to the volatility of the underlying asset. Vega is not the name of any Greek letter. However, the glyph used is the Greek letter nu instead of Vega or capital lambda. All options will gain value with rising volatility. Vega can be an important Greek to monitor for an option trader, especially in volatile markets, since the value of some option strategies can be particularly sensitive to changes in volatility. The value of an option straddle, for example, is extremely dependent on changes to volatility. Theta measures the sensitivity of the value of the derivative to the passage of time. The time decay, the mathematical result of the formula for theta, is expressed in value per year. By convention, it is usual to divide the result by the number of days in a year, to arrive at the amount of money per share of the underlying that the option loses in one day. Theta is almost always negative for long calls and puts and positive for short calls and puts. An exception is a deep-in-the-money European put. The total theta for a portfolio of options can be determined by summing the thetas for each individual position. The value of an option can be analyzed into two parts: the intrinsic value and the time value. The intrinsic value is the amount of money you would gain if you exercised the option immediately. So a call with strike $50 on a stock with price $60 would have intrinsic value of $10, whereas the corresponding put would have zero intrinsic value. The time value is the value of having the option of waiting longer before deciding to exercise. Even a deeply out-of-the-money put will be worth something. as there is some chance the stock price will fall below the strike before the expiry date. However, as time approaches maturity, there is less chance of this happening, so the time value of an option is decreasing with time. Thus, if you are long an option, you are short theta. Your portfolio will lose value with the passage of time. Rho measures sensitivity to the interest rate. It is the derivative of the option value with respect to the risk-free interest rate, except under extreme circumstances. The value of an option is less sensitive to changes in the risk-free interest rate than to changes in other parameters. For this reason, Rho is the least used of the first-order Greeks. Rho is typically expressed as the amount of money, per share of the underlying, that the value of the option will gain or lose as the risk-free interest rate rises or falls by 1.0% per annum. Lambda, omega, or elasticity is the percentage change in option value per percentage change in the underlying price, a measure of leverage, sometimes called gearing. Second-order Greeks. Gamma measures the rate of change in the delta with respect to changes in the underlying price. Gamma is the second derivative of the value function with respect to the underlying price. All long options have positive gamma and all short options have negative gamma. Long options have a positive relationship with gamma because as price increases, gamma increases up as well, causing delta to approach 1 from 0 and 0 from -1. The inverse is true for short options. Gamma is greatest approximately at the money and diminishes the further out you go, either in the money or out of the money. Gamma is important because it corrects for the convexity of value. When a trader seeks to establish an effective delta hedge for a portfolio, the trader may also seek to neutralize the portfolio's gamma, as this will ensure that the hedge will be effective over a wider range of underlying price movements. Vanna, also referred to as Vega spot and deltad, is a second-order derivative of the option value, once to the underlying spot price and once to volatility. It is mathematically equivalent to deltad, the sensitivity of the option delta with respect to change in volatility, or alternatively, the partial of Vega with respect to the underlying instrument's price. Vanna can be a useful sensitivity to monitor when maintaining a delta or Vega hedged portfolio, as Vanna will help the trader to anticipate changes to the effectiveness of a delta hedge as volatility changes, or the effectiveness of a Vega hedge against change in the underlying spot price. If the underlying value has continuous second partial derivatives, then Volga, Vega convexity, Vega gamma or DTAU, DVOL measures second-order sensitivity to volatility. Voma is the second derivative of the option value with respect to the volatility, or, stated another way, Voma measures the rate of change to Vega as volatility changes. With positive Voma, a position will become long Vega as implied volatility increases and short Vega as it decreases, which can be scalped in a way analogous to long Gamma, and an initially Vega neutral, long Voma position can be constructed from ratios of options at different strikes. Voma is positive for options away from the money, and initially increases with distance from the money. Charm or delta decay measures the instantaneous rate of change of delta over the passage of time. Charm has also been called delta time. Charm can be an important Greek to monitor when delta hedging a position over a weekend. Charm is a second-order derivative of the option value, once to price and once to the passage of time. It is also then the derivative of theta with respect to the underlying's price. The mathematical result of the formula for charm is expressed in delta, year. It is often useful to divide this by the number of days per year to arrive at the delta decay per day. This use is fairly accurate when the number of days remaining until option expiration is large. When an option nears expiration, charm itself may change quickly, rendering full-day estimates of delta decay inaccurate. Veta, or Vega time, measures the rate of change in the Vega with respect to the passage of time. Veta is the second derivative of the value function, once to volatility and once to time. It is common practice to divide the mathematical result of Veta by 100 times the number of days per year to reduce the value to the percentage change in Vega per 1 day. Vera measures the rate of change in ρ with respect to volatility. Vera is the second derivative of the value function, once to volatility and once to interest rate. Vera can be used to assess the impact of volatility change on ρ hedging. Third-order Greeks. Color, gamma decay or Dugg-Limit time measures the rate of change of gamma over the passage of time. Color is a third-order derivative of the option value, twice to underlying asset price and once to time. Color can be an important sensitivity to monitor when maintaining a gamma-hedged portfolio, as it can help the trader to anticipate the effectiveness of the hedge as time passes. The mathematical result of the formula for color is expressed in gamma year. It is often useful to divide this by the number of days per year to arrive at the change in gamma per day. This use is fairly accurate when the number of days remaining until option expiration is large. When an option nears expiration, color itself may change quickly, rendering full-day estimates of gamma change inaccurate. Speed measures the rate of change in gamma with respect to changes in the underlying price. This is also sometimes referred to as the gamma of the gamma or Dugg-Limit spot. Speed is the third derivative of the value function with respect to the underlying spot price. Speed can be important to monitor when delta hedging or gamma hedging a portfolio. Ultima measures the sensitivity of the option VOMA with respect to change in volatility. Ultima has also been referred to as VOMADVOL. Ultima is a third-order derivative of the option value to volatility. ZOMA measures the rate of change of gamma with respect to changes in volatility. ZOMA has also been referred to as DeGammadVol. ZOMA is the third derivative of the option value, twice to underlying asset price and once to volatility. ZOMA can be a useful sensitivity to monitor when maintaining a gamma-hedged portfolio, as ZOMA will help the trader to anticipate changes to the effectiveness of the hedge as volatility changes. Greeks for multi-asset options. If the value of a derivative is dependent on two or more underlyings, its Greeks are extended to include the cross effects between the underlyings. Correlation delta measures the sensitivity of the derivative's value to a change in the correlation between the underlyings. Cross gamma measures the rate of change of delta in one underlying to a change in the level of another underlying. Cross Vanna measures the rate of change of Vega in one underlying due to a change in the level of another underlying. Equivalently, it measures the rate of change of delta in the second underlying due to a change in the volatility of the first underlying. Cross Volga measures the rate of change of Vega in one underlying to a change in the volatility of another underlying. Formulas for European option Greeks. The Greeks of European options under the Black-Scholes model are calculated as follows. Where is the standard normal probability density function and is the standard normal cumulative distribution function? Note that the gamma and Vega formulas are the same for calls inputs. For a given stock price, strike price, risk-free rate, annual dividend yield, time to maturity, and volatility,